In this video, we're going to derive expressions for power gain using two-port S parameters. In the last video set, we used ideal voltage amplifiers to help us define what power gains were and observe some of their behavior, but we usually use S parameters to characterize two ports, including amplifiers, so it's important that we convert our intuition for power gain into expressions that are usable with S parameters. We're going to calculate the same useful power quantities we did in the last power gain video, then calculate power gains with them, but we'll use S parameters instead of real resistances this time. However, we're going to skip a lot of the derivations here because they're not terribly insightful. It's mostly a lot of unexciting algebra relating gamma values to Z values. I'll link up a full derivation of those powers on my website, but we're going to spend our time trying to get some insight into the physical meaning of each of the terms in the power expressions, instead of trying to infer those from a derivation. We're also going to take a look at what those powers actually look like when ZS and ZL are matched to lines, because that's usually what you see in lab. One preliminary, we're going to make some claims about conjugate matches later on this slide, and specifically we're going to say that gamma S equals gamma in star under conjugate matching conditions. That doesn't quite match what our result was from the previous videos, where we achieved a conjugate match by making gamma S match gamma dp star. So these power gains are usually derived by assuming that transmission lines are zero length, or equivalently you could think that these transmission line impedances, whatever the transform they provide, is going to get lumped into ZS. So we're effectively looking at a Thevenin impedance back into the transmission line. So assuming that we're lumping the transmission line into the source or into the load, we're going to say that gamma S is equal to gamma in star is a conjugate match, and gamma L equals gamma out star is an output conjugate match. So starting our analysis with PS. The power delivered from our source is the difference between the power in the A1 wave and the power in the B1 wave, and we can express that in terms of gamma in if we want to eliminate B1 from the expression. So we skip the derivation of referring that back to VS, but we can take a moment to understand what each term in the equation means. This first fraction represents the power launched into the line. The second represents some kind of conversion factor between A1 and VS. And the third is the 1 minus gamma in squared equation that we saw in our starting point. When we match ZS and ZL to Z0, this middle term falls away because gamma S goes to 0. And so we're just left with a wave power multiplied by 1 minus S11 squared. And this is S11 instead of gamma in, because you'll recall that gamma in is made up of S11 plus a round trip wave that goes out to the load and then bounces back. So if gamma L is 0, then gamma in is equal to S11. This is kind of an interesting expression, right? Instant power times some kind of matching factor that captures power bouncing off of the S parameter network. So we can think of it when S11 is high, we can't deliver power to the network, and that's captured by this term. The power available from the source is just the A1 wave that it launches. And again, we skip the derivation of how to get back from A1 to VS, but it's worth noting that this constant is very similar to this constant. And in fact, you get from one to the other just by noting that gamma in is equal to gamma S squared when we're doing a conjugate match to gather all the available power. To gamma S star when we're doing a conjugate match to gather all the available power. And so this gamma in squared turns into a gamma S squared. This gamma in turns into a magnitude of gamma S squared. And we can cancel a bunch of stuff to wind up with this expression. Then when we match the input and the output, we get back to a nice pure expression saying that the power available from the source is basically A1, is the power that we're launching onto the line. The power to the load is given by the power in the B2 wave minus the power of the A2 wave. And we can express that in terms of gamma L if we want to eliminate A2 from the expression. But we have a long way to go to get back from A2 to VS. And so skipping most of that journey, we find a big expression for PL that's made up of the instant A1 wave a A1 to VS conversion factor, something that kind of looks like a gain. This, S21 is the forward gain of the S network. This is maybe some kind of power gain. And finally, a term that reflects the quality of our match at the load. When we match ZS and ZL, we see that the input and output mismatch terms fall away, leaving only the instant power multiplied by our gain-like S21 term. This makes some sense. The power delivered to the load is given by the input multiplied by some kind of power gain in the network. And back in our full expression, that gain is degraded by matching quality at the source and the load. Finally, the power available to the load is just given by the power in the B2 wave. And dragging that back through our terrible derivation relates B2 to the driving voltage source. We see that power available to the load is given by the instant power multiplied by an A1 to VS conversion, sort of like our source matching factor, multiplied by our power gain, and then multiplied by a load matching term. But the big difference here is that the load matching term is different than PL because we are assuming a conjugate match. So we've replaced our gamma L's here with gamma out stars. And that gamma out term down here becomes important when we match the input and the output. In PL, this S22 value fell out of the equation because gamma L was 0. But in PAVL, since we assume a conjugate match, this gamma out star doesn't necessarily go to 0. It in fact becomes S22 star. And so the magnitude of S22 remains a part of our PAVL expression because we are accounting for the conjugate match at the load. In effect, this power is saying if you have non-zero S22 in your network, that will degrade the power you can deliver. So we're going to give our power expression a boost by 1 minus S22 squared to cancel out, to indicate what a conjugate match would do for you, to cancel out that degradation. Whew, that was a lot. I've copied our final matched powers over to this slide so we can start figuring out power gains. I've also copied over our power expressions from our previous power gain video, and we're going to compare those at the start of our analysis here. And then we're going to start building up gains and compare those as well. So let's start with the powers on this page. There are some really direct comparisons. For instance, PS is an input power reduced by an input matching term here and here. And PAVS is just some kind of input wave power here and here. Nice. PL and PAVL are a little harder to compare. In our sort of DC PL expression, we see that there's an input matching term and an output matching term, degrading our overall power. Whereas in our S parameter expression, there are no S11 or S22 terms, so what gives? Well, we can look to PAVL for a little bit of insight. PAVL cancels out the effect of a non-ideal S22 value down here, sort of as we discussed on the previous slide. And it does that by putting a correction factor of 1 minus S22 squared in the denominator. So that suggests for S parameter expressions, we can assume that we're ignoring a matching condition if we see a correction factor in the denominator. So in this PL example, there's nothing in the denominator. We have no correction factors. And so that means we are accounting for both the input and the output matching, or we'll be penalized by both the input and the output matching, which is the same behavior that we see on DC. Whereas PAVL cancels out the effect of a non-ideal S22 value, just like PAVL does when it takes this RL over ROut plus RL fraction and replaces it with a half that turns into a quarter in this expression. So this 1/4 is kind of doing the same thing as this S22 boosting in PAVL. So now that we've seen that the powers are kind of doing the same thing, let's look at our power gains. So GP here is PL over PS. That gives us S21 squared over 1 minus S11 squared. And previously we made the claim that GP, our power gain, ignores input matching network. It kind of forgives a bad input match. We saw that over here because there was no input matching term in our DC expression for GP. We see that here because we boost out the effect of our S11 mismatch. By having this 1 minus S11 squared term in the denominator, we are canceling out whatever power loss we get from a poor match to the line. And just like in our DC case, that comes because we're comparing the power to the load to this already reduced power from the source. Whatever gets into our amplifier is already reduced by the reflection factor in S11 squared. For transducer gain, we don't see the same correction factor, and that's because PAVS isn't reduced by the same input match that PS is. So we're comparing the power we deliver to the best possible source power we could receive. And this is analysis to our DC transducer gain expression, where we are affected by both the input and the output matches, and again, where we compare PL to PAVS. So transducer gain forgives neither a poor S11 nor a poor S22. Finally, for available gain, we see that there's a clear connection between our S-parameter expressions and our DC expressions, and that connection explains that the expressions care about the same thing. Finally, for available gain, we see we're correcting for S22 but not for S11. And this matches with our DC GA expression. Here, we care about the quality of our input match. Here, we forgive our output match, but we don't forgive our input match. So in both cases, the input match matters, the output match is forgiven, or doesn't appear. So summarizing, we see that there's a clear connection between our S-parameter expressions and our DC expressions, and that connection implies that each expression cares about the same thing. GP neglects the input match, GA neglects the output match, GT accounts for both types of matching. We also see the same nice behavior in that all gains collapse to the same value, which is S21 squared, if the network has a perfect input match and a perfect output match. So S11 is 0 and S22 is 0. And to be clear, that's a perfect input match to the line and a perfect output match to the line. Okay, so earlier we took a shortcut by assuming ZS and ZL were matched to Z0, but we could still find power gains if we allow ZS and ZL to take other values. They're just more complicated. So the transducer gain here can be derived by dividing our full unmatched PL and PVAVS from 2 slides ago. The math is uglier, but you can see this reduces to the magnitude of S21 squared if gamma S and gamma L are 0, so great, that matches our intuition. But another interesting way to interpret this expression arises in networks where S12 is 0, which are called unilateral networks. S12 being 0 makes power only flow from port 1 to port 2 and never from port 2 to port 1. If that's the case, then we can rearrange the terms in the GT expression into something called a unilateral gain. So we knock this out, we move this factor below this one, we move this factor below this one, and we're left with something that appears to depend only on gamma S and S11, so sort of the input side of our S network, a power gain S21 squared, and something that depends on gamma L and S22, so the kind of output side of our network. These quantities are referred to as mismatch factors. And you can picture a power trying to get into the S-parameter network through the source mismatch, getting scaled by S21 squared, and then trying to get out of the network through the load mismatch. One takeaway here is that the unilateral networks are desirable. At minimum, they make analysis and design easier, but it turns out they're great for stability, which we'll talk about soon. However, trying to completely squash S12 often has difficult trade-offs with bandwidth. So as a result, a lot of effort is spent getting bandwidth or S-parameter sensitivity. As a result, a lot of effort is spent getting S12 in just the right spot. Finally, if we assume ZS and ZL are conjugate matched to the line, GTU becomes GTU max, this expression down here. So this gamma S turns into an S11 star, and that turns into the magnitude of S11 squared. Ditto here, some terms cancel. GTU max is a nice upper bound on the performance of S networks. This is about as much gain as you could get out of it. And like before, we can also find this maximum unilateral transducer gain by dividing PAVL by PS. If you go back to the previous slide, you'll see it falls out of that same division. So in summary, power gains are easy to express in S parameters when the source and load impedance are matched to the line. We get these four equations, which are important and you're going to use all the time, especially the transducer gain that comes up a lot. It's just S21 squared. And like last time, our power gains have certain behaviors. The transducer gain is the most pessimistic, and the other gains boost out mismatch factors at the input or the output, or both in the case of our maximum unilateral transducer gain. And all of the gains reduce to S21 squared if S11 and S22 are 0. So that is, the input and the output are matched to the driving transmission lines.